Bismillahirrahmanirrahim. Now this is the second part of the lecture where we'll just focus only on helical compression spring, and I'm going to refer to it again by HCS. Let me change the color of the pen again to the green. Now here first I'm going to talk about the dimensional parameters, then I will talk about the stresses in helical compression spring, and the third thing that I will talk about the deflection in helical compression spring. So let's look in the dimensional parameters. So here we'll take a sample spring and we'll see what are the parameters that we need to define a standard helical compression spring. So here is a typical spring. This is the cross section of the spring that you see over here, and this is the spring. You can see that there is an outer diameter of the spring and there is an inner diameter of the spring, which is from the inner side, and this is from the outer side. This is the outer diameter of the spring, this is the inner diameter of the spring, and in between we define a diameter which is called the mean diameter of the spring. The distance between the two similar points on a spring is called pitch. So this is the pitch, and this is the wire which is used to make the spring. This is the spring wire diameter. Now when we wrap it like this, so here it's one coil, I am second coil, third coil, right? So there are total number of coils in this spring is NT that we count from here. One coil, two coil, three coil, four coils, 5, 6, and this is the last coil. And here you can see it is made flat, and we'll talk about the end conditions later. Here no force is applied on the spring, so we call this LO, which is the free length of the spring. So in summary, if we just look at it, D is the wire diameter of the spring, means the wire which is used to make a spring, what is its diameter? D is the mean coil diameter. One round of helix is called one coil. One round of helix is called one coil. This is the inside diameter of the coil, as you can see from here to here. This is the outer diameter of the spring coil. This is the free length of the spring, which is the overall length under unloaded condition. No load is applied. This is the coil pitch. This is the total number of coils. And then we define another parameter which is called NA, which is the number of active coils. And we'll soon see what do we mean by active coil. You look at it over here, the end, it's flat. It's just basically flat. But it's not necessary. We can have basically with the different end conditions. One we call plane end, one is called square and ground end, one is called squared and closed end, one is called the plane end and ground. So show you here, you look at it over it, the spring is just cut, nothing is done to the spring. This is called plane ends. Here the number of active coil is the same as number of total coils. Now you see the difference between the active coil and a what you call total coil. Actually it is the number of active coil which is, this is used in calculation. When it is a plain ground end, so what is done, it is just on the edge, it is made flattened over here. So what you are doing, you are removing half of the coil, means over here, half of the coil here. So the active coil is total number of coil minus 1. This is called plain ground ends. When it is a squared end, right, then it is again cut it, but one of the, you look at basically over here, the difference between the way it is cut over here, it is called square ends, and the active coil is total number of coils minus 2, and the last one is the square and ground ends. Now, why we need this? We need this to determine if the total number of coils are known, to determine active coils, to determine total coils if active coils are known, vice versa. And this table in your book, it basically provides all the information for 4 conditions: plain, plain and ground, squared and closed or closed, and squared and ground. So if the end coils 0, 1 and 2, these are the end coils, they are not useful. Total coils and active coils are equal, but here you see the total coil is active coil plus 1, because this is there. Here again it is added, here it is added. This is the free length, which is, you can calculate pitch times the number of active coils plus the wire diameter and so on. And this is the length, the solid length, and this is how you determine the pitch of the spring. So let's see how we determine, knowing basically now the nomenclature, the end conditions, and the different lengths of the spring. Let's take a spring. A compressive load is applied onto the spring. The mean coil diameter is D, and the wire diameter of which the spring is made is the small d. So in other words, capital D is the mean coil diameter, D is the wire diameter, and F is the force which is acting on the spring. This is not a shear force, this is a compressive force. It will produce shear force, and we'll see it later. Now next, what we would like to see, how we will use this force, and using from the knowledge of statistics, not statistics, statistics is from the course of statics. So this is the force. So I'm going to cut the spring, and I will replace over here this force and another force. So when I replace these forces, what I'm going to see, I'm going to create a moment with the two forces by this distance, and that moment is the torque over here, while this force will pass through the section and it is parallel to the section. So now this force is called as the shear force. Here we are applying as a compressive force. So the same F will become a compressive force, but when we do the force analysis, this force on the wire itself will become a shear force. Now what will happen? There will be a shear stress on this as a result of this shear force, and there will be another shear stress because of this torque. So there are two shear stresses that will basically appear on this spring. So what are those? the two shear stresses. One is because of the torque, TR over J, and one is because of the force, which is F over A. A is the cross-sectional area of the wire, and J is the polar moment of inertia. T is the torque acting on the spring, and R is the wire diameter, wire radius, half of the wire diameter. Now, if we say the maximum torque is tau, the radius is half of the wire diameter, polar moment of inertia is pi d4 by 32, and the area is pi d square by 4, we can write, substitute all of these in this equation. All of these, if we substitute here, we can simplify it, and you can see that the stress depends on shear force, mean cold diameter, wire diameter, and shear force. This is the stress in a helical compression spring. Right? What we have is the Ks that you can see over here. But now we have the wall factor. We go further, so we have this wall factor, but there is another way to determine the curvature effect, and I'm going to talk this later. Let me skip this one. Next slide, and we say the other one is called Bergstrasser factor, and that says that the shear correction factor is this. The difference between these two, wall factor and Bergstrasser factor, is 1%. So what is done, that we find a curvature correction factor by the ratio of the two, and we do basically this, right? We can use it as a curvature correction factor, and what we will do basically, we'll use this equation, or we will use KW8FD over pi d cube. Now, how we determine the deflection in a spring? To determine the deflection in a spring, first what we will do, we will determine the total strain energy. And how we'll do the total strain energy, because there are two different types of shear forces over there, so I will have to calculate the two different components of energy. One which is originating from the torsion effect, and one which is coming from the shear force effect. So this is because of this shear force, and this is because of the torque that is on this. Now, what we can do, we can substitute. We know already torque is this, the length is basically this one, the J is this, and A is this. We substitute all of these, and that becomes the equation for the U. Now, why basically the equation for the U is important? Because according to Castigliano's theorem, if we take the derivative of the U with respect to the deflection, right, then we will get force. And if we take with respect to force, we will get deflection. So since we want to find the deflection, what I have to do is to take the derivative of this with respect to force. So when we take the derivative with respect to force, we get this equation, and this equation defines the what we call the deflection in a helical compression spring when a compressive load F, which you have seen at the beginning, at the top and bottom, is applied. Now again we will use the spring index, and when we use this spring index, the equation can be combined to this. Now you look at deflection is equal to 8F capital D cube, which is the coiled diameter, N is the number of coils, and D is the wire diameter, and G is the shear modulus of the spring material. Now, one interesting thing from this, F is here, Y is here. If I take F over Y, what I'm going to get? I'm going to the spring rate of the spring, which is small d raised to the power 4 times shear modulus divided by 8 coil diameter raised to the power 3 times the number of coils. Now we will go and look at few of the issues before we go and see how to design springs against static and dynamic loads. One is the stability or buckling and critical frequency. So the helical compression spring can buckle, means it will become unstable when the deflection becomes too large. So in other words, the spring is like this, and what will happen when you apply the load, and if I just fix it, it may go like this. It's buckling. And I need to basically prevent it in my design. So I need to find out what is the critical deflection of a spring. The critical deflection of the spring is given by this equation, where this is a free length, C1 and C2 prime are the constants which depends on the material parameters. Lambda effective is dependent on the alpha, which depends on the end condition. L0 is the free length, coil diameter, and L0 has to be below this. If the free length is below this, then the spring will not buckle. As I told you, alpha will depend on the end conditions, and it is given in table 10.2. If the deflection is more than the critical deflection, then a spring will become unstable. In a very simplified form, from all these equations, what we can find out for steel, if the free length is less than 2.63, right, d over alpha, right, then what will happen, let me just basically quickly back again. Now here this shows that if your free length is less than this parameter, your spring will not buckle. And as I said, D is the mean coil diameter, and alpha will depend on the end, plane end ground, squared end, and squared end ground ends. The other you can see from here, that's a very nice graph. This is not in your available in book, and I have taken from some other sources. You see over here, this is the ratio of free length to the mean diameter, and this is the ratio of deflection to the free length, and you plot it basically over here. And the graph is plotted for the two kinds. One is, you look at both ends, they are parallel. If you look at it over here, that this is fixed, but now it's not parallel. If you look at this to this, they are not parallel. So this is for parallel ends, and this is for non-parallel ends. So this one is for this case. And what it says, if you plot this and you have this, anything which goes above the curve, it is unstable. And if the point lies below the curve, then it is stable. And same is true basically for the non-parallel ends. The last thing is about the critical frequency of the helical compression spring. The natural frequency or critical frequency of the helical compression spring is equal to this or this. Depends on if one end is fixed against a flat plate and the other end is free, then this is the equation. If one end is fixed against a flat plate and the other is driven with a sine wave motion, then this is the equation. Where K is the spring stiffness. We have the equation before. G is the gravity. And W is the weight, which you can calculate it using this. So what is the conclusion? The conclusion over here for the frequency is that the fundamental critical frequency must be greater than 15 to 20 times of the frequency of the force or motion of the spring in order to avoid resonance. In other words, let's see, you have critical frequency F, you calculated, which is, let's say, 100. And now you are going to apply a force, a motion to the spring. What you need to do, you have to reduce it by 15 to 20 times. So if I divide 100 by 15, that's about 6.5 or 6.6 or 6.7, and 100 divided by 20 is 5. So I can maximum apply from 5 to 6.7 hertz if my fundamental frequency of the spring is 100 hertz. And I need to do this so that the resonance will not occur. The last one is the spring rates. What we have yet talked about is only the springs, which are one spring. If the spring is in series, then you can find the effective stiffness of the spring by using this. And if the spring is in parallel, then you can find the effective stiffness of the spring by using this. Here, K is the spring rate. So with this, we conclude